Judith, shall we begin?
Hagai?
Yes. Here. Okay, everyone.
Yeah.
We can start.
So I'll introduce you, Hagai.
Yeah, and the camera is the camera of the room, so we can see me and other people as well. But it's I think it's good because we're feeling some kind of small conference here, and me and Moshe and his group. It's great. This morning I asked Bered if I should come or should we do it from the office, and she said, "Come." Good idea.
So while you set
So
up
I'm
your
going to talk
camera,
about my.
yeah, while you set up your camera, I will introduce you. So now for the final presentation, please welcome Dr. Hagai Shpigler from the Department of Entomology at ARO, who worked together with Dr. Tzipora Teitel from the Department of Food Science at the Gilat Research Center ARO. Dr. Shpigler, the floor is yours.
Thank you so much. Just when we start, we're going to talk today. I'm going to talk about the projects that we have done for the last 3.5 years, almost from the beginning of the war. We're going to talk about bumblebees and how to protect bumblebees from viral infection in the pollen. I will explain why it's important. My collaborator, Tzipora Teitel from Vulcani as well, she joined us about a year and a half ago. She's doing some chemical analysis of pollen. And Mike Simon Feinstrom from the USDA at Baton Rouge. Mike was a great help for this project because first I went to visit him in his lab in the USDA lab, a wonderful and beautiful lab of just dedicated to honeybee. 8 different researchers sitting there and studying honeybees, and I learned so much on how to do viral work. For me, it was new. I came from a different field in bees, and it was a great help. He shared with us all of his protocols and methods. And I have to say, I wish we could achieve more in this project, but I don't think it's the end today. I just will present what we achieved now. So our hero here on the top, you can see the bumblebee. This is the bumblebee. It's the local bumblebee of Europe and Israel. And you can see pollen grains in the middle. Let's continue for the next slide. And so the bumblebee industry is a very interesting story. It started about 45 years ago. It wasn't an industry. People didn't grow bumblebees. It started somewhere in Belgium and in Holland in the beginning of the 80s. They found a way to grow bumblebees indoor inside rooms. And suddenly you have pollinators that can bring out mostly to greenhouses in the beginning. Today it's spread all over. And today it's in industries that was billions of dollars. And there was they grow millions of colonies every year. I think just in Europe, about 2 or 3 million colonies. In Israel, hundreds of thousands of colonies. And the was in the value in pollination, it's huge, billions of dollars. So this is a pretty new story in agriculture. In Israel, the biggest companies that produce bumblebees is BioBee from Australia. They are the first one to adapt this technology, and it's also the supporting company for this project, which also gave us a great help because BioBee are really ready to share with us the data and to help us and whatever we need, bees or pollen, the supply for this work. Also, I have to say there is another company in Israel that produce bumblebees. It's from Yad Mordechai. It's called Polyam. And also, I have to say this was a nice collaboration. As also were ready to share data and to help us because the problems that we tackle, it's something that everyone is and anyone in this industry is facing. So let's continue with the introduction, very short one. So the bumblebees are crucial for pollination service. And millions of bumblebee colonies are grown in factories every year, not just in Israel, all over the world. By the way, in the US, it's a different species. They use a local one from the US. Pollen serve as a primary source for protein in the industry. So to grow bumblebees, we need to bring pollen. But the pollen, if you want to bring pollen from outside, there is no mechanical way to collect it. We need to collect it by using honeybees. honeybees are standing outside. They collect the pollen on their leg. This is why it looks like small grains. They put them on the legs. There's batches of pollen. When they come to the colony, we put traps. It fall down and we can collect the pollen. The problem is pollen is you can collect only in the spring, only 2 or 3 months a year. There is pollen outside, and you need to keep it in the freezer the whole time. So this is a product that you cannot produce whenever you want. The second problem is that if the factory is inside and you grow your bumblebees inside, the only way of pathogens to introduce into these factories is by pollen. Pollen is the main route that coming from outside inside. Now, the sugar waters that fed to bees can be sterilized easily. It's produced by the companies that don't need any artificial thing to do. But the pollen is a natural products that need to come from outside. The common use is to use gamma radiation to sterilize the pollen. In the beginning of the project, we sought to build a new way to sterilize the pollen, maybe use ozone, but several papers that came just in the beginning of the project convinced us not to continue on this line, but to understand what's happened with the pollen after gamma radiation and how we can protect the pollen. I will talk about it. So when we talked about how to protect bumblebee from viral infection, we started on 2 routes of research. If this is the pollen, first we wanted to understand what is the viral load and what is the threshold of viral that need to be in the pollen to infect bees. So there is always something inside. The question is it enough? Can it infect bees? And this is a very important question because and pollen it's hard to buy and it's not much outside. This is a hard market, and the companies need to buy whatever they can. And when they bring it in, the question is, do they bring inside these viruses? And if they are inside, can they infect the bees? Yes or no? And there is also a bureaucratic question here, because when they want to export a bumblebees from state to state, they check them if they have any pathogens. And the thing is, if you take a bee and you do the test using PCR, qPCR, it's very, very sensitive. And even if there is just a bee viruses inside the pollen, they come in the gut of the bees. They are not infecting the bees, but they can be detected. And they say, no, your colonies have the viruses inside, and then they can be stopped, the export. And so this is the question: are your bees infected, yes or not? And we wanted to look if there is a threshold, and we wanted to look in a real life scenario, not just in a different way. I will talk about it in more. The second direction was to check what is the gamma radiation doing to the pollen, and is it affecting? Does it decrease the nutritional level of the pollen, and why? So we showed some results that we have, not everything that we have, because we're working on it for more than 2 years. And yeah, we have some beginning and stop with all the war around. We had some problem with personnel, but we succeeded some. So the experimental design was, in my head, built as real world condition. This was important for me to give the real conditions that can be expected to see in the company. So first, we look for infection via pollen feeding. Most of the research on bee viruses are including injection of the virus or feeding through sugar water. And this is not the scenarios that anyone in real life will see. So we try to give it in the right way, in the ways that can solve the problem. So infection via pollen feeding. It's also need to be a continuous feeding. They need to feed it, usually when they feed the viruses, the sugar water, they give one drop, one time. But we gave them all the time. We gave them a pollen infected with the virus for a long time, for 5 weeks, just to see when the infections happen. We test the infection in workers, and not just when you look at bees, you can see workers, you can see larvae, you can see queens. We wanted to check the whole levels because virus can find different routes to get inside. We quantify viral load not just in the gut, because the gut is infected with, you can find the viruses straight from the pollen. And we wanted to look at on inner tissues just to make sure that the bee is being infected. So we look also on the fat body, which is the liver of insect. So we opened our bees after the experiment, and we took two tissues, the gut and the fat body, to see if there is a real infection, a systemic infection. We tracked the infection over time, not just after one time feeding, but after a week and after 5 weeks. We showed the results. So this is the result. We jump in straight to the result without much methods. So what you can see here, we used one virus. It's called Israeli acute paralytic virus, and we used group of 12 bumblebees, 12 workers. And on the left, the first one, the control, is without viruses. We use evaluated pollen and we spiked it with the IAPV. The low, it's 10 in a 3. It's about 1,000 particles of the virus inside 1 gram. The medium, it's about 10,000. It's a bit more, it's 10 times more, and the high is even higher. And what you can see here, we have two tissues. We have the digestive system, it's the blue, and we have the fat body in red. So here we get nothing. This is the logarithmic scale. And when you go to the low, you see there is no difference from the low to the control. We see a bit more in the gut, and it's expected because we fed them with the virus. But when you go to the medium, suddenly you see a jump. You see that the fat body itself start to show infection. We can see the virus replicate there. So we have, this is after 1 week. And so there is a threshold, at least after 1 week. When we look after 5 weeks, we can see a similar picture. We were worried that the low will be infected after 5 weeks, because if you press enough and you give enough virus, even in lower levels, it will be infective. But what we found again, that the threshold for infection is around the medium. It's about 10,000 particles per gram of this virus, which is a very aggressive virus in this case. We also look on larvae that grow on this pollen. So we use young colonies, and there were larvae inside that were grown feeding only on this pollen, and we found again that there is a threshold. Again, the red is the fat body, and the digestive system in the blue was even higher. It's around here. It's about 10 in a 6 when we start to see the infection in the bees, and so we can say that there is a threshold. It can be quantified, and if you buy a pollen, you can check it before you feed, and to be sure that you won't be infected, at least with this virus, and other viruses probably need more checks. We also have done another experiment with queens. Here, this is the dichotomic response. Are they infected or not? We gave you 10 in a 3, 10 in a 5, 10 in a 7, 10 in a 9 for a long time. And what you can see is that we check here the gut, and you can see from 10 in 7, all of the bees are infected, at least in the gut, but the gut also pollen, but we see in the fat body as well. What was interesting is that we look on the ovaries, and if you look here at 10 and 7, you can see that there is a lot of virus also inside the ovaries, meaning that the virus can go vertically to the next generation, which can infect the factory for a long time because it's continuing with the bees. It cannot be stopped easily. The next direction that we took, it's about talking about the gamma radiation effect. So we took the pollen, and in this case, we bought pollen from BioBee. So they gave us control pollen that was not irradiated or irradiated in low level of 10 kilogray or high level of 20 kilogray. We took this pollen and we fed it to bees, to small colonies of bumblebees, and we look how they develop. This pollen is sterilized from viruses mostly. At least it goes to very low level. And we have done the first experiment after 1 month or after 4 months in the freezer and 10 months. And as I said, pollen need to be saved in the freezer for at least a year, and before you can get the next batch of pollen. And usually in factories, they keep it for 2 years. So this is a small microcolony with bees you put inside, start to develop their ovaries and lay eggs, and you can see how they develop. Here you can see eggs of bumblebees, and we count them, how many of them we can see after we fed them. So this is the result. This is the work of my one of my first master student, Itzik Sadeh. And here you can see this how much the bees fed. So on the left, this is the first month. You can see the control, the 10 kilogram and 20 kilogram. And After you can see the middle one is the 4 months and the 10 months. You can see there's a fed about the same in the beginning, but later at 10 months, all of the bees fed more. Probably the pollen, after being stored for long, need to be fed. The bees need to feed more on it to get enough nutrition. And we look on the number of the eggs. You see in the first months, there is no difference between the groups, but after 4 months, there is a drop in the irradiated pollen, and after 10 months, even more. The control keep it normal. When we looked on the number of males that they grow, when bumblebees lay eggs, they can develop into male when it's workers. So in the first months, we don't see any difference between the irradiated and not irradiated pollen, but there is a drop after 4 months and 10 months, meaning that the pollen is becoming less nutrition if you irradiate it and keep it in the freezer, even if you keep it in the freezer. Not just that we see less males, less bees coming out, but also the size. This is a measurement of the size, and you can see after 10 months, the size of these bees, of the males that develop on the irradiated pollen, is smaller. So, as I said, this experiment design were done as close to answer the questions that are really interesting for the company. Also, I have to say that the beginning of this project was when I took a ride to BioBee and asked them, what is the problems that keep you, make you the most problem? What is the thing? And they talk with me about this irradiation, what's going on there. And so we built this project. For now, what we're doing, we decided when we bought pollen and it was irradiated or not, was never from the exact same batch. So we collected our own pollen and we irradiated it now, just 2 months ago, and we start to track this pollen and from the chemical level to see what's happening, why it's less nutrition. And so first things that we do, we took a picture of this pollen under the microscope, and we used an Alexander staining that colored the hemolynx of the cells, with pollen cells. Here you can see beautiful cells of pollen under the microscope. It looks like small dots. But if we irradiate it, it's the same pollen, it's the same batch as well. If it's irradiated, you see everything is pinkish. And if you look well, you can see the hemolynx just coming out. So it means that when you irradiate pollen, you not just stabilize it, but you also change it. You break the cells walls and you see the change. And I want to share another piece that Tzipora was supposed to talk about the next slide. So this is the chemical analysis that Tzipora just had done and sent it to me. Yeah, she's around. Oh, she's here.
Yeah, can you hear me?
Yes.
Okay. Hi. So
You want to turn on your camera?
It's on. Can you see me?
Yes. Yes. Hi.
Okay. So our part of the project was to perform the chemical analysis to see whether there were any phytochemical changes to the pollen upon irradiation. And on the left, you can see the analysis that we did in the context of oxidation. So our hypothesis was that changes are related to oxidation status of the sample. So what we did was first we analyzed the antioxidant activity of the samples, and you can see here that the irradiated pollen had lower levels of antioxidants in 3 different assays, the ABTS, DPPH, and FRAP, and each of them actually evaluates different antioxidants in the sample. So you can see that all kinds of antioxidants were lower in irradiated samples. So that's one thing. Another thing was the T-bars here. I'm not sure you can see my cursor, but the T-bars, it indicates the oxidation, level of the oxidation, free radicals in the sample, and you can see that the level of oxidation was actually higher in the non-irradiated samples. Also, you can see here on the bottom left, let me, it's wouldn't, okay, I can see it. So that's the peroxide value. So the peroxide value was is another indication of oxidation, and it was actually again higher in irradiated level samples. So it means that in general, irradiated samples had more oxidation. They were experiencing more oxidation consequences, probably due to the radiation. And then if you can load the next panel. So here what we evaluated were the levels of specific antioxidants. So if on the left we were looking generally in antioxidant activity, here we were evaluating specific phytochemicals such as polyphenols and flavonoids and anthocyanins that are supposed to increase the antioxidant capacity of the samples to contribute to the antioxidant activity. And you can see that the polyphenols level is lower in the irradiated samples. Here we saw that the polyphenols and anthocyanins were actually higher, but since both flavonoids and anthocyanins are subgroups of polyphenols, so it means that other polyphenols were probably lower, although these specific groups of polyphenols were not affected by radiation. So that concludes what we did in the in the chemical part. You can move on to the next slide.
Okay, so let's go to the conclusion here. So far, we found that there is an infection threshold via pollen. It starts at around 10-fold, so 10,000 particles of IPV per gram of pollen. It can be measured, and then it can be say if the pollen is safe or not. The influence can transfer vertically from into the eggs. Pollen irradiation leads to decline in pollen quality. We see it in the development of the bees, and also we see the vessel. We see some oxidation and activity inside the pollen after the irradiation. I will conclude with thanks. So first, for the supporting company to BioBee, this is Elad Zohar, is the main researcher of the bumblebees in the company, and Shimon Steinberg, the main researcher. The former main researcher of BioBee today, it's Yoni Eran. Both of them help. All of them help a lot to make this project happen. Mike on the left from the USDA, it's Pora and me. And down here you can see my lab manager Elad, Dorka, which is a postdoc working on this project today. Itzik is my first postdoc working, and my first master student working on it. I have to say, Itzik was doing 300 days of reserve force duty. We also had Shoval later. She came for 2 months, and then she was called on duty as well, and she left. Myself, I was doing 200 days, and Elad was doing tons of days. I think more than me, 400 at least. Isabella, she's the lab manager of Tzipora, and Yasmin is also a master student working on this project. That's it. Thank you for listening.
Thank you, Hagai, and thank you for all the presenters. Are there any questions for Hagai? If not, then we conclude our free presentation, and thank you again for sharing your work with us. Have a good day. Thank you. Questions? You did?
Let me just look at the chat just a second.
I haven't seen any.
No. So, okay. So thank you very much, everyone. Have a good day.
Thank you. Bye-bye.
I have a question about the bumblebee. Is that the most common bee in Israel?
Yes, it became very